In the last video, you were introduced to superdense coding, which is a way for Alice in this communication protocol to send 2 bits of information using a single qubit. Teleportation is in some sense the opposite. It allows Alice to send 1 qubit with 2 bits of information. The protocol is very similar, using the same sets of gates, so I'll just draw out the circuit and we'll perform an analysis of the circuit rather than what we did in the previous video, which was kind of reverse engineer what we wanted to achieve with the superdense coding circuit. So in this protocol, I didn't have a beautiful quantum rainbow. Affectionately named quantum teleportation works like this. Alice has a qubit. It's an arbitrary state. She wants to send to Bob. There are 3 qubits involved in this protocol. Alice has the first 2, and Bob has the last one. And just like in superdense coding, what Alice and Bob are going to do initially is create some entanglement. So in all of these protocols, Alice and Bob need to get together and coordinate some strategy. Now that strategy includes them creating an entangled pair of particles, one which is kept by Alice and the other retained by Bob. Now Bob, he just goes along his merry way, kind of indefinitely. Alice has some work to do still, so what she's going to do is perform a measurement. And just like Bob had to disentangle this encoded pair of qubits, one of which was sent by Alice, Alice here has to kind of swap this entanglement now from the original qubit she had with Bob to this other qubit. So she's going to perform a measurement, and she's going to send the result of the measurement to Bob. Okay. So we're going to have some like classically controlled operations. And just like in the superdense coding protocol that we just saw in the last video, we're going to perform an X and a Z. And the claim is, which we're going to have to show, is that Bob ends up with the original qubit that Alice wanted to send. Okay, so Alice had this qubit up here, Bob initially had 0, and he ends up with the qubit that Alice originally had. And this depends, what he does depends stochastically on the 2 bits of information that Alice sends. So Alice might record a 0 or 1 outcome for either of these 2 qubit measurements. She sends those 2 bits to Bob, and then Bob, he might not do anything at all. So he may just leave his state alone, in which case he already has the state psi sitting with him, or he might have to perform some operations, this X and Z operation. Now the way in which typically we analyze circuits is by drawing some vertical line and numbering these points in time. Remember that when we looked at the Circ programming language, these were called moments in time. Okay, so we have 1 through 5. All of this happens before the measurement. Then a measurement happens, and Alice will send some bits to Bob, and Bob will have to potentially change the state of his qubit or not. So at time 1, we have psi, which can be written in the computational basis. So this is an arbitrary state psi. And then we have 0, 0. So psi 0, 0 is alpha 0, 0, 0 plus beta 1, 0, 0. All right. Now, a Hadamard is applied to the second qubit. So the second qubit is going to go from 0 to plus. So now we're at 2. Just to be concrete about it, we have I, H, I acting on the state here. And so we have alpha, and that's going to go to 0, 0, 0. Let's not forget the 1 over root 2 plus alpha 0, 1, 0. And a similar thing happens over here. We have beta 1, 0, 0 plus beta 1, 1, 0. Okay, so that Hadamard took that 0 to 0 plus 1 with the 1 over root 2 factor. And so in each of these terms, we kind of expanded things out. Now we have a C naught at step 3. Let's give this a name. Let's call that psi at step 2. So now we have C naught applied to psi at step 2. So the conditioned on the second qubit, we're going to flip the third qubit. So we have alpha over root 2, 0, 0, 0. That doesn't change. Alpha over root 2. And now we have a 1 in the second position, so the third one has to change. Beta 1, 0, 0. In this case, the third qubit doesn't change because the second qubit is 0. And finally, we end up with beta 1, 1, 1. Okay. All right, so now this sort of, at this point in the protocol, Alice and Bob have created entanglement. Now Alice and Bob separate, and between step 3 and step 4, Alice is going to perform some operations on her 2 qubits. So the first 2 positions in the ket belong to Alice, and then there's this implied tensor product, and Bob has the qubit in the 3rd position. Wherever Alice might be in the world, she has her 2 qubits next to each other, so she can perform these operations and then perform measurements. So at step 4, okay, remember this is now, let's call it psi 3, we have C naught, and if we wanted to be explicit, we could have said C naught from 1 to 2, and here we have C naught from 0 to 1. Acting on psi 3. So if the first bit value is 0, then we flip the second bit value. Or if the first bit value is 1, we flip the second bit value. So nothing changes there. Nothing changes here. And now we're going to see some changes. So we have 1 beta is 1, 1, 0 in that first ket, and then the second ket goes to 1, 0, 1, 0, 1. And let's call that psi 4. And finally we have another Hadamard acting on the very first qubit. Alright, so here we can do some simplifications to help us with this calculation, so that otherwise we're going to double the number of terms, which we don't necessarily want to see. So let's factor out the 0 in this first one. So we have 0, and then we're left with 0, 0 plus 1, 1. And on the second one, we have a 1 in the first position, and then we have 1, 0 plus 0, 1. Now we're going to apply this Hadamard to this state, psi 4, because that just takes that 0 state in that first position and creates a plus state, and the 1 state in the second term and creates a minus state. So we have alpha over 2 now, 0 plus 1, 0, 0 plus 1, 1, plus beta over 2, and we have 0 minus 1, 1, 0 plus 0, 1. Okay. Alright, now we're going to perform a measurement. So the measurement is going to result in one of 4 outcomes. So either Alice will see 0, 0, 0, 1, 1, 0, or 1, 1. Let's expand this out. Then we're going to have a big 1 over 2 sitting up front, and then we're going to have alpha 0, 0, 0 plus alpha 0, 1, 1 plus alpha 1, 0, 0 plus alpha 1, 1, 1. And let's start a new line here for the betas. Beta 0, 1, 0 plus beta 0, 0, 1 minus beta 1, 1, 0 minus beta 1, 0, 1. And let's see here. We have 8 terms, and we've covered all the basis states. We have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, good. So we have 8 basis states, and Alice is going to perform this measurement. The measurement is specified by the first 2 qubits. So Alice will see one of 4 possibilities, either 0, 0, 0, 1, 1, 0, or 1, 1. We can look at all 4 possibilities. So if Alice sees 0, 0, that happens with some probability. So the probability of 0, 0 is specified by all of the coefficients squared of only those cats with 2 zeros in the first entry. So we see 1 here and 1 here, and so that's alpha over 2 squared plus beta over 2 squared, and this is equal to 1 over 4 and alpha squared plus beta squared. And what are alpha and beta? Those were the original coefficients of the qubit that Alice wanted to send. So those have to sum to 1, so that's with probability 1/4, Alice will see 0, 0, and the state that she'll be left with is alpha 0 plus beta 1. Okay, so she sees 0, 0. What's left in the third qubit is alpha 0 plus beta 1. That's actually equal to psi. So if Alice performs a measurement, sees 0, 0, then Bob already has psi sitting there in his qubit. So whatever this physical system, it's representing this state psi. Alice might see 0, 1. That will happen with probability. Okay, so let's look for 0, 1. We see 0, 1 here and here. And perhaps you are about to see some pattern emerge. We have alpha squared plus beta squared. And those are 1 over 4 each. So again, this is 1 over 4. And the state will be left in alpha 0 plus beta 1. Oh, sorry. Let's double check this. Alpha 1, beta 0. That's the third bit in these cats. So alpha 1 plus beta 0. Because that's not quite psi. However, you can see that the bits have just been flipped. So this is equal to x acting on psi. So if I act x on psi, then I'll flip the 0 to 1 and the 1 to 0, and I'll get alpha 1 plus beta 0. How about 1, 0? Again, the probability is a quarter. Now let's find those 1, 0 cats. Let's see here. Different color. 1, 0, 1, 0, okay. And we have alpha 0 minus beta 1. Alpha 0 minus beta 1. Again, that's not psi. However, there's a minus 1 in front of that 1 cat, so that we recognize as a Z operator being applied to psi. And finally, Alice might see 1, 1, and well, these all have to add up to 1, these probabilities, so we know that that probability has to equal a quarter, but again, the pattern shows that we have an alpha and a beta and a 1/2, so we're going to get a quarter again. So the last two are this one here and this one here. So we have alpha 1 minus beta 0. Alpha 1 minus beta 0. Okay, so first, what do we want to do? How do we get psi back from this? Or what do we need to apply to psi to get this? So if we first apply an x, we'll flip those bits. And then if we apply a z, well, the minus would have gone in front of the 1, which is now sitting in front of alpha. So we don't want to apply x first. We want to apply z first, which puts a minus 1 in front of the 1, which was sitting in front of beta initially, and then we apply the x, which flips the bits. Okay. So Alice performs these measurements, and then she and, well, Bob, if he knew what the result of the outcome was, would know how to get back to psi. So if Alice sees 0, 0, Bob does nothing. Okay. If Alice sees 0, 1, whatever Alice sent to Bob, Bob has to apply an x to it. Okay. In which case, we'll apply x, and then x, and that to x times psi. X squared is equal to the identity, and we're left with psi. Okay, in this case, same scenario. Alice is sending him z times psi, or the qubit that Bob has is left in z times psi. Bob knows that because Alice communicates these two bits, 1, 0 to Bob to tell him what measurement outcome she got. And so this becomes z squared psi, which z squared is equal to the identity, and so this is also psi. And finally, Bob has to undo this operation. So first he's going to apply X, and then he's going to apply Z. And so we'll get, well, the X and the X squared to identity, and then we're left with Z squared, which is also the identity. Okay? So Bob needs to perform some operation conditional on what Alice sends. And we see that this is exactly what the circuit is showing up here. Bob conditions these X and Z operations on his qubit, depending on what Alice sends him. And so at point 6, Bob deterministically has psi. The bits that he receives are uniformly distributed, so each of them has probability a quarter. But once Bob performs the required operation, he ends up with psi in the third qubit of this protocol. Okay, so that's teleportation. I would say some people like the name. It's a bit of an unfortunate name. You can decide on your own how you think about it. It's not like teleportation that you see in the movies, in sci-fi movies. So Alice has some description of a qubit, some state of a qubit, and some correlation between her and Bob, and she communicates some information so that the qubit that Bob has should be assigned the same original state that Alice had. And information is not being copied here, remember, because Alice ends up with one of these 4 basis states. So she no longer has psi, Bob now has psi, so no information has been copied. Some interesting things can happen with this protocol. Alice, she may have actually had an entangled state, not psi, but some other larger state that was entangled with maybe another party, Charlie. So Alice and Charlie may have shared an entangled state, and after the protocol, Bob and Charlie will now have an entangled state. So if Alice, I'm going to make a mess here of my diagram, but oh well. Say Alice and Charlie had some entangled state, then at the end of the protocol, Bob doesn't have psi anymore, but in fact has an entangled state shared between he and Charlie. And it can get even more interesting. Charlie could have another entangled state with Diane, perform a teleportation protocol with Diane, and once that teleportation protocol is complete, Alice and Charlie no longer share any entanglement, but Bob and Diane share entanglement. And this is called entanglement swapping. A schematic of what's happening is probably easier to see. With Alice and Bob and Charlie and Diane. We have Alice, Bob, Charlie, and Diane. And Alice and Bob, they initially share some entanglement to perform their protocol, teleportation protocol. Alice has 2 qubits. She wants Bob to end up with her second qubit. Charlie and Diane have the same scenario. They share some entanglement. Charlie is going to perform a measurement on his 2 qubits, communicate that classically to Diane, and then Diane is going to end up with the state of her qubit being the original state of Charlie's second qubit. Now let's imagine that second qubit for Alice that she wanted to communicate to Bob and Charlie were initially entangled with each other. After the protocol, the entanglement shared between Alice and Bob go away. In some sense, they use it up. And similarly, between Charlie and Diane, they use up this entanglement to communicate, to perform the measurement and then communicate the classical information. But what also happens is that the entanglement between Alice and Charlie disappear, and now appears between Bob and Diane's qubits. So Alice performed the teleportation protocol with Bob, Charlie performed the teleportation protocol with Diane separately. Alice and Charlie at some point met, created an entangled pair, each of which was going to be the ones that they were going to use in the teleportation protocol. After the protocol, Bob and Diane now share that same entangled state, even though they had never met. So you can imagine how this would be very useful if we want to distribute entanglement across, say, a quantum internet. So that's superdense coding and teleportation, the first two communication or computational protocols that you've seen in the subject.